So please take it away, Thomas.
Okay, well, thanks a lot. Well, first of all, thanks a lot for the invitation. It's an honor to speak here, and thanks for the organizer for putting together this conference. In this talk, I will talk about a minimal structure for the string landscape, and it will be based on a number of papers. Some of them are still to appear. I list them here, and it's worked together with Pries Bastian, Damian van de Heijsteek, Erik Blauschien, and three mathematicians, Christian Schnell, Ben Bakker, and Jakob Zimmermann. And let me just point out this paper here, well, it's kind of the state of the art of these applications of Hodge theory to the string landscape. And if you look for someone who is really an expert, please keep your eye out to Pries and Damian, especially this fall. So let's get started. My talk will have three parts. In the first part, I will talk about moduli stabilization. More precisely, I will quickly point out four lessons which we have learned in the past years about the complex structure moduli space and moduli stabilization. And in fact, the upshot of this is that the scalar field spaces and the scalar potentials in type 2 flux compactifications are remarkably constrained. In the second part, I will briefly discuss a very non-trivial finiteness result for the landscape. Namely, I will point out that the constraints from the structure of these potentials are just enough to ensure that there are only finitely many self-dual flux vacua. And finally, in the third part, I will explain a little bit how one proves this and kind of what is the underlying structure which makes this work, right? And this underlying structure is so fascinating that I believe that it is something which we should maybe consider to impose on the complete landscape. So just to give you already some words on this, in fact, my title is not as vague as it sounds. There are, in fact, in mathematics, there is something which is called an O-minimal structure, and I will propose that we use such O-minimal structures to describe the landscape in general. But let me first start with these lessons we learned in the last years about flux compactifications and the complex structure moduli space. So what are these compactifications? Well, in this audience, I don't have to spend too much time in explaining the details. I will talk here about type 2b flux compactifications with three-form fluxes, and they satisfy a Tadpole condition. And the flux vacua which I will study are the ones which satisfy this self-duality, this vacuum condition, which is displayed here. They have a well-known lift to F theory, where the flux is then in the G4 form flux, a 4-form flux, which is quantized or half quantized, which satisfies again a Tadpole condition. And the vacuum condition in this case is just this self-dual condition here. I think it's fair to say that these are the most well-studied vacua with n equals to 0 and n equals to 1 supersymmetry, and which partially fix complex structure moduli. We understand backreaction very well. We know that it's kind of just a warp factor and the Calabi-Yau condition stays intact and so on. And even higher derivative constructions, corrections have been taken into account, at least in the M theory setting, which is dual to this F theory situation. So the state of the art on these kind of corrections is appeared in this recent paper. So what makes these vacua interesting? Well, there is the Hodge star appearing here, which changes over the complex structure moduli space, and it's in general very complicated. However, we know that the complex structure moduli space has boundaries, so it's not compacted. It has boundaries and it has asymptotic regimes, and the hope is that at least in these asymptotic regimes, we can understand what happens to this Hodge star and the geometry in general very explicitly. Let me give you an example. What do I mean by boundaries? So this would be kind of a cartoon of the moduli space of the quintic. And you see that it has two, or in fact, it has three boundaries: the conifold point, the large complex structure point, and also the orbifold point. So this is what I mean by boundary. It's exactly there where the manifold degenerates or does something really drastic. Yeah? And the near boundary regime, these asymptotic regimes, are then the regimes close to these points in the moduli space. Just to give you an idea, when we talk about the large complex structure point, then you can also use mirror symmetry and go to the large volume point. So the large complex structure regime is actually dual to the large volume regime. And maybe many of you have a lot of intuition about what happens in the large volume regime. And this is exactly one special case of what we want to understand here, but it's much more general than this. In fact, the situation gets really, really complicated if you think about the complete complex structure moduli space. I depicted here for this mirror Calabi-Yau, which is kind of this well-known example. And then the complex structure moduli space has this fancy form, and it has a lot of boundaries, so a lot of degeneration loci. There's a large complex structure point, there's a conifold locus, but things can intersect and funny things can happen to the manifold. Yeah. So what do we want to achieve with with our study is we want to get a systematic understanding of these asymptotic moduli spaces without scanning through examples. Of course, you can just construct the manifold and compute everything, but it would be nice to understand what is really behind all of this. And then once we do that, we want to identify the states, kind of D-brane states, for example, or the flux value, at least in this asymptotic regime. And then we want to test conjectures, because we know there are certain conjectures which are supposed to hold inside these asymptotic regimes. I listed some of them here, and it's interesting to test them using these insights. Let me kind of be very bold and add a conjecture here. I would say that in order that a swampland conjecture is true, it has to be at least satisfied in this type 2B settings, right? So this is my confidence in the setting conjecture. So I have a lot of confidence that what we are doing in these settings is actually true and can be used. And so, and therefore, of course, I'm not alone in this. I think we all agree on this. And therefore, there has been a lot of work in doing tests on this conjecture in these settings. And I tried to list names, and I finally gave up because there's a lot of work in the market, but there are excellent reviews on this, and I refer you to them. Also, Timo gave a very nice talk on Monday, and there is certainly some overlap in the techniques here. So what are the tools which we used? We developed tools using asymptotic Hodge theory. This started already quite some time ago, but at least for me, it only becomes now clear how powerful these things actually are. And I hope I can highlight this in this talk with the few lessons which I want to list. So what is the first lesson which we learned is that actually there exists a classification of boundaries. So on each codimension n boundary in complex structure moduli space, we can introduce a split of the middle cohomology of a Calabi-Yau manifold of dimension d into a PQ decomposition and a decomposition into representations of SL2 to the nth power, where n is this codimension. So just to give an example, in a one moduli limit, so in a one moduli boundary, there is just one SL2, and then we know the SL2 representation theory, and we find that that there is a PQ decomposition on the boundary. So even when this manifold is very wildly singular, you can still define a PQ decomposition, and you can define a decomposition into spins of this SL2. And in fact, these two decompositions, they are compatible. And in higher dimensional moduli spaces, you have multiple SL2 spins, but still we all know how to deal with these sort of things, right? This is just representation theory. And what's the upshot of this? You actually find a classification of the boundaries using SL2 representation theory. And what is non-trivial to impose on this representation is positivity of the Hodge norm, right? And if you combine these two things, you actually get a complete classification. Let me give you an example. For a one modulus Calabi-Yau threefold moduli space, we find three types of possibility: the conifold, Turing degenerations, and the large complex structure points. So this is relatively easy to check. When it becomes more and more non-trivial, the more and more moduli you have, as you would expect, right? From the picture I gave you before. And in fact, already in the type, if you have two moduli, there are in fact 16 possibilities. But whatever example you study, you will always find one of these 16 possibilities, or no degeneration. Yeah. And in fact, if you look into the recent literature, like small W0 literature, for example, you find that these were exactly studying these type of boundaries. People who embed Seiberg-Witten theory into string theory, they use these type of boundaries. And the large volume cases appear all in the Kreuzer-Skake list. You can really scan through the Kreuzer-Skake list with two moduli, you will find all of these cases. So they are actually even realized in actual geometric examples, even so this classification is more abstract. Now, what is this useful for? You can use this to approximate the Hodge star in any geometric regime, in any asymptotic regime. And what you find is that the behavior of the Hodge star is just given in terms of these SL2 spins. So this is really the leading behavior of the Hodge norm at any of these boundaries. Yeah, you have to impose some ordering of the coordinates, some kind of growth rate of these coordinates, and then what you find is exactly this very nice, simple, universal behavior. Yeah, and since we classified all of these limits, you can obtain all possible asymptotic behaviors. So this is the most crude approximation, but it's very easy to handle, right? You can learn already a lot about the various limits. Now, what we learned more recently, and that's quite exciting actually, this machinery is so powerful that you can not only reconstruct this leading behavior, but you can also start to include subleading correction. And this can also be can be used to derive the period, so the integral of the three form of the D0 form, the 3-0 form for Calabi-Yau 3 form, for example. So what is the boundary data? Well, obviously, first of all, it's the SL2 data and this boundary PQ decomposition, which we mentioned already is classified. And it's not only classified, you can also write down simple normal forms of each of them. Then you have to supplement some extra data, which we call phase operators. And we know their properties, but they are not fixed. They are only fixed if you look at a specific Calabi-Yau manifold. But we know quite a lot about them, and so we can use the most general ansatz, which is compatible with the boundary data. And if you combine this and some of this technology, then you can reconstruct the Calabi-Yau threefold periods. And what you actually find is that you get the polynomial corrections in these periods near every boundary, and also the essential exponential corrections. So these corrections you can never drop without ruining your field space metric. Yeah, so they are very essential, and therefore they can be also obtained from these Hodge theory techniques. Yeah. Just to give you an example that this is not just words and general blah blah, it's really something you can do. Yeah, even so it's technically quite involved. So I give you here an example how the period, some finite distance periods look like near the boundary, and it's just these complicated expressions. And at infinite distance, it's a two moduli example, the conifold LCS class examples, and you see the general form of these periods look like this. And the idea is you can do that for any, in principle, you can do that for any number of moduli and reconstruct them abstractly near any boundary. So what is the fourth lesson which I wanted to highlight is that this provides us with a new procedure to find flux vacua as well. So recall this was the self-duality condition, and now how would you solve such a condition? Well, you can either use a computer and solve these heavily complicated expressions, or you can invent some approximation scheme. And what this Hodge theory techniques tell you is that there is a very nice approximation scheme. Namely, you first start with the SL2 story, where everything is polynomial and very easy. It's very easy to find vacua. You can almost do it by hand, even for many moduli. Then you can go to the next approximations. You can include these corrections, and you get a refinement of the vacua. And then you can include all the exponential corrections. So in the middle step, you have only these essential exponential corrections, and then you go to full story. Of course, I should mention, this is a very, this has many advantages. For example, you can think about hierarchies and so on. So you can have a flat direction in the SL2 approximation, which is stabilized in the next step, kind of including the next two leading corrections. So it's nice that this is an algorithmic approach, and in fact, you can almost do it abstractly, but even if you apply it to example, it has favorable numerics, yeah, because you already have a starting point where to search vacua. It naturally implements vacua, and you can discuss all these things which have been discussed here before. And the nice thing is you can also do it for a large number of moduli and fluxes. So you can address conjectures which are very, very hard to test if you just do it by hand. Okay. Now, these are the lessons which I wanted to communicate, and now I want to use this understanding to actually prove some of these conjectures, or one of these conjectures which is there for a long time, namely the finiteness of self-dual flux vacuum. So what do I mean by self-dual flux vacuum? I look at an integral flux which is self-dual and has distractible conditions, but I fix the Calabi-Yau manifold. So I assume that there are only finitely many Calabi-Yaus. So the evidence for finiteness has been given some time ago, but so that's now hard to communicate. There was no complete proof. Yeah, so even so, there was a number of 10 to the 500, 10 to the 200,000, whatever. You know, these were very crude approximations were used to get these numbers, and it was never shown that they are not somewhere like an infinite tail of vacua. So what would be the idea to show that there are actually only finitely many of them? You have to show that on every path to every boundary, only finitely many vacua can arise. So that's the same type of problem like you need to address in the distance conjecture. But here you can do it, right? You can do it really on, at least you can try to do it mathematically concrete, because the objects are very clean. So it can be done for codimension 1 boundaries. You can really implement this. You can look at every path near the boundary, and you can use these SL2 techniques. However, unfortunately, the general story is much more complicated. And to highlight this a little bit, it has been done in a famous paper by these 3 mathematicians for 2,2 fluxes, which are SUSY fluxes, as we know, but mathematicians would call them Hodge classes. And there is a famous theorem which uses these SL2 techniques to control every path on every boundary. However, they use holomorphicity. And for our self-dual fluxes, this discussion is much more, but it's a level more complicated. So you cannot use holomorphicity because these are not SUSY vacua in general. Yeah. And so what is the way to do it, and what's the way how we are doing it? Well, we have to use a recent breakthrough in mathematics, which combines a field of logic, like some ideas from logic, and topology into Hodge theory. And these tools are called, it's called tame topology. And there's
Right,
this,
Thomas, you've got 5 minutes in your main talk.
yeah, and there's a famous paper by Bakker, Klingler, and Zimmermann who prove a number of conditions on using these techniques. And I will not explain them in very much detail, at least not in 5 minutes, but the important statements are that you can endow the appearing object with something which is tame. And tame, you can think of it really in the same sense of the word, that it kind of removes strange things and infinities. Yeah. And in particular, they show that this period map is actually some sort of tame map, and they use these SL2 techniques. And so how do we proceed? Well, we say, well, this Hodge star and the G4, we want to study their properties. Well, you can think of this Hodge star living in a coset and the fluxes to live on a lattice. And if you combine these two things with the self-duality and the tadpole, you actually find there are only finitely many pairs of subsets of the moduli space and the flux lattice, which can occur. So this really proves the finiteness of these vacua using this connection with tame topology. Now, to give you a little bit of flavor of what that means, let me introduce this to a minimal extent in a few minutes. Okay. So recently there has been a lot of discussion about finiteness in the landscape, and it started with these early works here, but more recently there are a number of papers which I tried to collect in this slide. So how would you go along with this? So what do mathematicians do? Well, you first start with a real line and you think about what are the finite sets on the real line which you want to highlight. Well, you could have finitely many points, finitely many intervals, or infinitely long intervals, but just finitely many of them, right? And then to describe this, you can describe this with functions. For example, a polynomial function has just finitely many zeros. But a sine function doesn't have finitely many zeros, and you don't want to include it. Yeah. So if you construct your landscape out of sine functions, they will automatically, or your potential out of sine function will automatically have infinitely many zeros. And what mathematicians manage is they actually promote this finiteness into a structure. And the structure now consists of subsets of the real numbers. And then you allow for finite intersection and finite unions. And so it's a very complicated object, but it's tamed by a single condition. And this condition is that on the real line, the structure reduces to intervals, finite intervals, and points. So exactly what I showed in the picture before. Okay, and this is it's a remarkable way of formulating a new approach to geometry, because it kind of has finiteness built in, and it realizes one of Grothendieck's dreams of what a tame topology in the real sense of the word is. There are some recent results on tame topology, which I don't want to discuss in detail, but the crucial point is there are well-known examples of these O-minimal structures. They can be constructed by using the exponential function, or including the exponential function. So instanton corrections are something which is kind of allowed. And that's exactly what is in this recent paper, that exactly the period map is exactly in such a O-minimal structure. And kind of relating it to some old work by Acharya and Douglas, they made some nice discussion about how do I deal with a potential which is a sine and has these properties and so on. And what one actually proves here is that this can never happen. Yeah, what they were thinking about. It can never happen in an actual landscape of type 2B, at least. So what is my conjecture to conclude the talk is, so if we think about the set of effective theories and viewing then as kind of a points here in this figure. Everyone in the swampland community has to show this picture once. And I make for each of these moduli space, the rank of gauge group, a matter spectrum. Then my conjecture is the following: the string vacuum landscape is definable in this O-minimal structure. Yeah, and this is certainly true if I believe my conjecture one for these type 2B settings, which are very non-trivial. And the nice thing is, this structure is so general, it's non-trivial, but it's also very general, that it also includes non-supersymmetric vacua. It doesn't rely on holomorphicity or all of these things which you can easily criticize in the analysis. So this leads me to conclude. In the first part, we uncovered the structure of the complex structure moduli space, and without the need of scanning through examples, and we are ready to make proofs for some of the recent conjectures. We already proved something mathematically exact, namely the highly non-trivial finiteness result of self-dual flux vacua. And at the final part, which admittedly was a little bit abstract, but maybe over the years, if we understand it better, then we can actually use these O-minimal structures to describe the string theory landscape, which have built-in finiteness and are general enough to construct, to include non-supersymmetric configurations as well. Thank you very much.
Great, thanks very much, Thomas. That was a very interesting, and you covered a lot of ground, although a finite amount, I guess, of ground. So let's see, we have a question from Severin.
Hi, yeah, thank you, Thomas, for the very nice talk. So this is probably a bit of a naive question, but if I understand correctly, the strategy for showing the finiteness of vacua is to see that there's not an infinite number of vacua when approaching one of these boundaries of the moduli space. Is it evident? How can I see that there's not an infinite number of vacua or flux configurations which in the bulk of the moduli space?
Yeah, this is relatively easy to see, because if you look at the Tedbook condition, right, and you say that the flux is self-dual, then G wedge G becomes G wedge star G. So the only possibility that there could be infinitely, and G wedge star G is positive definite. Mm-hmm. So the only possibility where there could be infinitely many vacua is when the Hodge star degenerates. And the Hodge star degenerates almost by definition only near the boundary. So that's one of the conjectures where the boundary is all there is. I mean, where all the non-trivial thing is on the boundary or is near the boundary. Yeah.
I see.
And by the way, this is a misconception, I think. So if you think that you have to go to the bulk and then everything is kind of complicated and non-understood, keep in mind that on the moduli space, you're dealing with holomorphic functions. So all the fancy things are kind of encoded near the boundaries. Or most of the fancy things are encoded near the boundary. So sorry, you wanted to follow up.
I mean, in principle, I think I could imagine having a series of fluxes within the tadpole bound, where I don't know, I have some entry in the flux vector which is not bounded, which is not contributing to the tadpole bound, and which therefore in principle could take infinitely many values. Would that always drive me to the boundary?
Yeah, this is just not possible. That's exactly the statement of the theorem. So there are no self-dual vacua where the tadpole doesn't depend. I mean, doesn't blow up when you go towards the boundary.
I see.
So every tail is cut off at some point.
Mm-hmm. Yeah.
Otherwise, it would not be finite. And you see, this is very non-trivial. If one thinks about it for some time, it's very, very non-trivial. And therefore, we had to use all this technology. We tried it with direct uses, and it's just very difficult.
Great. I don't see any other questions on.
Can I ask a question? I can't raise my hand because of co-host, but can I ask a quick question?
Please go ahead, Fabian.
Yeah, so I just wanted to ask two questions. First of all, can you comment on extension to the models they've already constructed with infinitely many fluxes that drop out of the tadpole? And second question, unrelated, does this help you in sort of improving your finite results of counting points? Does this help you in improving the 10 to the 500 estimate? Or is it sort of, do you just know it's finite, but you cannot really say how many vector there are?
Well,
Sorry, Thomas, while you're answering, can you unshare? And so Angel can go ahead and put his slides up while you're answering the question.
sure, please. Yeah, of course, yes. Am I unshared?
Yes, thank you. Angel, please go ahead and share your screen while Thomas is answering the question.
Yeah, so first of all, you mean type 2A vacuum with these infinitely many
Yes, yeah.
solutions. Yeah. So we understood this already in a paper with Irene and Chongchu. What is kind of the type 2B analog of this if we kind of just brute force model this type of vacua? And what you realize is that you find you have to include, to kind of model this, you have to include fluxes which are not self-dual.
Yes, exactly.
And from the type 2B perspective, then the back reaction is out of control. So from the type 2B perspective, it's very clear why we maybe don't want to consider these. Yeah. Or at least then there are back reaction issues which you have to address. Yeah.
So you can't just, you cannot address them within the framework.
You cannot, you can address them in the framework, and you find some of these infinite tails, and then you have to do what one also has to do in type 2A to carefully think if one actually has the back reaction under control. Yeah, and if you want to hear my opinion, otherwise the conjecture wouldn't be true, which I was putting up. The back reaction is not under control near these boundaries.
Yeah, this is a tricky question. So I want to move on to Angel's talk. Thanks a lot, Thomas. I had a question too, but maybe we can move other questions offline to the Slack or email. And let's turn to our second talk, which is, thanks very much. Let's give Thomas another hand.